Hi everyone, Samar here, and welcome back to GoDevOps. So, in today's episode, we're going to talk about the container runtime. So, remember our restaurant analogy from the previous episode? We have the customer, that's the developer, the waiter, that's the Docker daemon, and actually behind the scenes, there's the cook, and this cook is the one that actually prepared the dishes. And in Docker, this cook is the container runtime. So it takes the orders from the waiter and turns the ingredients, images, and layers into a fully working container. So in this episode, we'll see exactly how this cook operates. So we'll be talking about the container runtime. So what is a container runtime? It's the low-level component responsible for creating and running containers. So it receives instruction from the Docker daemon and interacts directly with the operating system to start container processes. There are three types of container runtime, and we'll be starting with the high-level container runtime. Here we have two examples. And they actually act as the main coordinators between high-level tools such as the Docker daemon and Kubernetes, and the low-level runtime that actually creates and run container processes. So in Docker's case, we have the container RD, and it's used internally by the Docker daemon to manage containers and images. And in Kubernetes, we have the CRI-O or Container RD, and they are used as the runtime backends through the Container Runtime interface. So rather than sitting above the Docker daemon, these runtimes are the core components in the container execution chain. So think of them more of the middle manager in the container work. So they organize, they prepare, and delegate work to the lower layers. So here's what they handle. Um, they handle image management, so pulling images from registries, caching them locally, managing snapshots, container lifecycle, so creating, starting, stopping, pausing, and deleting containers. Communication layers, so providing a stable API to interact with. And we have also extensibility, so supporting plugins and or extensions for logging, monitoring, and security, making them flexible for different environments. Just let's clear up a common confusion. So the difference between a daemon and a high-level runtime. So a daemon is simply a background service. So it keeps running, listen for requests, and manage things continuously. For example, the Docker daemon is a daemon, only a daemon. But here's the important part. It's not a runtime, so it doesn't directly create containers. It delegates that job to something else. A high-level runtime, on the other hand, it's a component that manages containers. So it handles images, snapshots, and container lifecycle. But in practice, most high-level runtime are also implemented as daemons because they need to be always running on the background. So here in this diagram, we have in the middle we have tools like Container RD and CRI-O that are both daemons because they run as a background service, but also they are high-level runtime, so they manage images, snapshots, and container lifecycle uh, while passing the actual work to the low-level runtime. And on the left, we have something like the Docker daemon, which is only a daemon, but not a runtime. And on the right, you see the pure high-level runtime that doesn't actually exist in the practice, because to actually manage containers properly, they need to act as daemons too. So they need to be running as a background to see what is actually happening in the container. Now let's see the low-level runtime. So it's the final component that takes all the instruction from the high-level layers, so like container spec, namespace, C groups, and mounts, and they actually create the container process on the host system. So it doesn't deal with images, registries, or container lifecycle management. Its job is much simpler. So it translates the container specification into kernel level isolation. So in other words, it's the piece that really starts the container. And we have in here the two most common low-level runtime. We have the runc, and it's the default for Docker and Kubernetes, and it's built by the OCE, and it's extremely widely adopted. And we have the new one, the crun, and it's newer runtime written in C, and it's optimized for performance and memory and a lower memory overhead. So it's becoming increasingly popular, especially in lightweight environments. So how does it actually work? It all starts with a high-level runtime that prepares the OC specification for a container. And that spec is handed off to a low-level runtime. And the low-level runtime calls Linux kernel features directly. So we have namespace for isolation, C groups for resource limits, and mounts for file systems. And finally, it launches the container main process inside the isolated container. So here we have that the higher level actually manage the life and the organization of the containers, and leaves the low-level runtime to do the actual creation of the container process in the operating system. Now let's look at another category of runtimes, the specialized runtimes. So these are designed for scenarios where security and isolation are just as important as performance. So here we have three examples. Let's start with the first one, the gVisor. And it's a sandbox runtime developed by Google. And instead of letting containers interact directly with the host kernel, it intercepts system calls and implements its own kernel in user space. So this means even if a container is compromised, the attacker doesn't have direct access to the host system. It's often used in multi-tenant environment where strong isolation is critical, like in Google Cloud serverless platforms. The second example is Kata Containers, and it takes a different approach. So instead of using only namespace and C groups for isolation, Kata runs each container inside a lightweight virtual machine. So these micro virtual machines provide stronger boundaries than namespace while remaining faster and lighter than traditional virtual machines. So it's a middle ground. You get the virtual machine level of isolation, but also the container-like speed and flexibility. And finally, we have the Firecracker, and it's a micro virtual machine that is created by AWS, and it focuses on being extremely lightweight and secure with minimal overhead. So it's perfect for a scenario where you need to run thousands of short-lived isolated workloads quickly. And so these specialized runtime are especially useful in cloud environments and multi-tenant systems where container isolation alone might not be enough. So now that we know what a runtime is, let's look at its core responsibilities. So we have the namespace and C groups. So these provide isolations. So the runtime instructs the Linux kernel to create separate namespace, so each container believes it's running on its own system. Then it applies C groups for CPU limits and memory and EU usage. We have the file system set up. So before a container can run, it needs a root file system. So the runtime takes the impact image layers, mounts them together into a unified rootfs, and exposes it inside the container. For networking, so the runtime doesn't always set up the network itself, so it works with higher level components or container network interface plugins to connect the container to virtual networks and namespace. For security features, so beyond isolation, the runtime enforces security boundaries. It can apply seccomp filters, enable AppArmor or CLinux profiles, and make sure the container cannot exceed kernel permissions. For lifecycle management, the runtime lends the container main process. Uh, it monitors to and stops it when needed, and cleans up the resources once it exists. Let's now look deeper into the architecture of container runtimes and how the different pieces fits together. So at the very top of this stack, we have the high-level runtimes, and their job isn't to execute containers directly, but instead they sit closer to Docker Daemon or Kubernetes and manage container lifecycle, pull images, and prepare all the data required to start a container. But when it comes to actually create the container, create the process, high-level runtimes hand things off to low-level runtimes. And the most widely used one is the runc, which follows the OCE runtime specification. And this layer is responsible for turning a container definition into a real Linux process using kernel primitives like namespace for isolation, C groups for resource limits, and mounts for file systems. Then at the bottom of the stack, we have the Linux kernel, and this is where the actual mechanism that makes containers possible live. So we have the process isolation, the resource control, the networking, and security hooks. And the runtime doesn't reinvent these. They just orchestrate how the kernel applies them for each container. Now there's also another category of runtime, which is the specialized runtime. And this is at the same level as the low-level runtime, but instead of interacting with the kernel directly, they insert an additional isolation boundary. So what we need to take away from this video is that, first of all, the runtime is really the engine that takes an image and turns it into a running container. We saw that there are three different types of runtime. We have the high-level runtime that handle life cycles and orchestrations. The low-level runtimes that create the actual container process using kernel features. The specialized runtimes that provide stronger isolation and security. And of course, everything relies on the Linux kernel, which provides namespace, C groups, and networking and security. And that's it for today's episode. If you found this helpful, make sure to like the video, subscribe, and hit the notification bell so you don't miss for future episodes. And in the next video, we're going to talk about the container images. So that's it for today's episode. Thank you and bye.